What if some of the best places to park a spacecraft are not around a planet, but in the empty-looking space where gravity is trying to throw you away? That sounds like a contradiction. Gravity pulls, orbits fall, empty space should not have parking spots. But when two large bodies move together, like the Sun and Earth, their gravity and their shared motion can carve 5 special places into space. They are not surfaces. They are not platforms. They are more like invisible ramps, ridges, and valleys in a landscape that only appears when you ride along with the orbit. To see them, imagine the solar system as a traffic problem. Put a star and a planet on a giant circular road. The star is huge, so it barely wobbles. The planet is smaller, so it sweeps around once per year. Now add a spacecraft with almost no mass of its own. It is too small to change the road, but it still has to obey the traffic. If you watch from outside, everything is moving. The planet never sits still. The spacecraft is always falling around something. The pattern is hard to read, so change seats. Ride in a rotating frame that turns once per orbit at exactly the same rate as the planet. In this view, the Sun stays fixed, Earth stays fixed. The line between them becomes a permanent road on the map. But this rotating view has a price. You have to add an apparent outward effect, the centrifugal effect, as if the rotating map itself is trying to fling objects away from the center. Now the spacecraft feels a combined terrain, the downhill pull of the Sun, the downhill pull of Earth, and the outward tilt from rotation. This is the landscape of the Lagrange points. In ordinary space, these points are empty. In the rotating landscape, there are places where the slope becomes perfectly flat. A spacecraft placed there with the right speed can keep the same position relative to the two big bodies, not because gravity vanishes. It does not. At a Lagrange point, gravity is still acting. The trick is that gravity provides exactly the centripetal acceleration needed to stay locked into the same rotating pattern. There are always 5 of these points in the simplified 3-body problem. 3 lie on the line through the 2 massive bodies. 2 make equilateral triangles with them. The first one, L1, sits between the 2 bodies. In the Sun-Earth system, it is about 1.5 million kilometers sunward from Earth. That is only about 1% of the distance from Earth to the Sun. At first, L1 seems impossible. A spacecraft closer to the Sun should orbit faster than Earth and drift ahead. But Earth's gravity pulls backward, away from the Sun, weakening the effective solar pull. The spacecraft can orbit the Sun more slowly than it normally would at that distance, matching Earth's 1-year pace. L2 sits on the far side of Earth, also about 1.5 million kilometers away. A spacecraft is slightly farther from the Sun, so by itself it would orbit more slowly than Earth. But Earth's gravity adds to the Sun's pull. The extra inward tug lets it keep up. L3 is on the opposite side of the Sun from Earth, slightly outside Earth's orbit. It is the old science fiction hiding place for a counter-Earth. The geometry is neat, but the point is not a good hiding place, and not a good parking place. It is unstable, difficult to observe from Earth because the Sun is in the way, and any real object there would be perturbed away. Then come L4 and L5. They do not sit on the Sun-Earth line. They ride 60 degrees ahead of the smaller body and 60 degrees behind it, forming 2 huge equilateral triangles. If Earth is one vertex and the Sun is another, L4 and L5 are the other possible vertices. These are the 5 parking spots. But the word parking is misleading, unless we ask the next question. What kind of parking lot are we talking about? For L4 and L5, the answer is a broad, shallow valley. This is where the traffic problem becomes more than a diagram. If a small object near L4 or L5 is nudged, it does not simply fly away. In the rotating landscape, the path curves. The Coriolis effect, another apparent effect from the rotating frame, bends the object's motion around the triangular point. Instead of rolling straight down a slope, the object loops, drifts, and can become trapped in tadpole-shaped paths around L4 or L5. The result is not a single parking space. It is a neighborhood. Jupiter shows this on the largest scale. Its L4 and L5 regions contain the Trojan asteroids, 2 great swarms orbiting the Sun with Jupiter. One swarm travels about 60 degrees ahead of Jupiter, the other trails about 60 degrees behind. Astronomers have cataloged many thousands of Jupiter Trojans, and the total population larger than a kilometer may be in the hundreds of thousands, possibly more. They are not sitting perfectly still at a mathematical point. They librate, meaning they oscillate around the stable region. From the rotating point of view, they trace loops, like cars circling inside a large mountain basin, without quite finding the exact center. This only works when the mass ratio is favorable. For the triangular points to be stable in the ideal problem, the larger body must be more than about 25 times as massive as the smaller one. The Sun and Jupiter easily qualify. The Sun and Earth do too. Even Earth and the Moon qualify. That is why Trojan companions are not rare oddities. Mars has Trojans, Neptune has Trojans, Earth has at least 2 known Trojan asteroids, including 2010 TK7 and 2020 XL5, though Earth's swarms are small and hard to observe from our position. NASA's Lucy mission is built around this fact. Launched in 2021, it is visiting multiple Jupiter Trojan asteroids, using them as time capsules from the early solar system. L4 and L5 are not just parking spots, they are storage shelves. Over billions of years, stable regions can preserve old material that would be scattered elsewhere. But stability is not the same as stillness. The valley is wide, the motion is complicated, and the objects keep circulating. A Trojan asteroid is parked the way a boat is parked in a slow whirlpool, confined but never frozen. Now compare that with L1 and L2. These are not valleys, they are mountain passes. If L4 and L5 are basins that can hold swarms, L1 and L2 are narrow saddle points in the rotating landscape. Move in one direction and the slope pushes you back. A spacecraft exactly on the point would be balanced, but exact balance is not something the real solar system offers for long. Solar radiation pressure pushes on spacecraft. The Moon perturbs the Sun-Earth system. Planets are not perfect points. Thrusters are imperfect. Even a tiny error grows. So spacecraft do not usually sit directly on L1 or L2. They orbit around them. That sounds strange because there is no planet there to orbit. But near a Lagrange point, the combined gravitational and rotating geometry allows halo orbits and Lissajous orbits. These are looping paths around the empty point, like circling a traffic island that is made of mathematics. L1 is useful because it gives an uninterrupted view of the Sun. The Solar and Heliospheric Observatory, SOHO, has watched the Sun from near Sun-Earth L1 since the 1990s. DSCOVR also sits near L1, monitoring the solar wind before it reaches Earth. From there, charged particles streaming off the Sun can be measured roughly tens of minutes to about an hour before they arrive, depending on their speed. It is an early warning checkpoint for space weather. L2 is useful for almost the opposite reason. From Sun-Earth L2, the Sun, Earth, and Moon all stay in roughly the same direction in the sky. That makes it easier for a telescope to keep its cold side cold and its instruments shielded from heat and light. The James Webb Space Telescope operates near Sun-Earth L2, about 1.5 million kilometers beyond Earth. It is not hiding in Earth's shadow. In fact, it avoids passing through the shadow because it needs stable sunlight for power and thermal balance. Its giant sun shield keeps the hot side facing the Sun, Earth, and Moon, while the telescope looks outward into deep space. Other missions have used L2 for similar reasons. The Planck Observatory mapped the cosmic microwave background from there. Gaia has been measuring the positions and motions of more than 1 billion stars from an orbit around L2. Euclid is also stationed near L2 to study dark energy and cosmic structure. So the fragile points are not failures. Their instability is part of their usefulness. They are like exits on a freeway interchange. You do not go there because the pavement is flat forever. You go there because many routes are close together. This is also why L1 and L2 are valuable staging areas in mission design. In the Earth-Moon system, Lagrange regions are important for low-energy transfer paths. A spacecraft can use the geometry to change destinations with less fuel than a brute force route might require. The landscape has ridges and corridors, and careful navigation can use them. But every parking metaphor has a limit, and L3 is where the limit matters. L3 is the tempting trap. It looks, on a simple diagram, like the most mysterious Lagrange point. Put Earth on one side of the Sun, put L3 on the other, and you have a perfect place for a hidden twin world. The old idea is visually irresistible. but the rotating landscape around L3 is also a saddle. It is unstable like L1 and L2, without their practical advantages. For the Sun-Earth system, it sits behind the Sun from our perspective, so communication and observation are awkward. Worse, gravitational tugs from other planets, especially Venus and Jupiter, disturb the arrangement. A counter-Earth at L3 would not remain neatly hidden. It would drift, and its gravitational effects would give it away. L3 is a parking spot only in the narrow mathematical sense. In the real traffic system, it is a lane that looks empty because no one can safely stay there. This is the deeper answer to the opening question. The best places to park in space are not always near solid objects, because near is not the only thing that matters. What matters is the shape of motion. Two massive bodies do not just pull on space like isolated wells. Together, in a rotating frame, they sculpt a map of possible motion. Some places are shallow basins that can collect asteroids for billions of years. Some are passes that spacecraft can circle with small corrections. One is a seductive dead end, symmetrical enough to invite stories, unstable enough to erase them. The Lagrange points are hidden because nothing marks them. No rock, no beacon, no visible ring in the sky. But they are real in the way a current in the ocean is real. You know it exists because things gather there, drift there, or need only a little steering to remain there. Space is often described as empty. The Lagrange points reveal a stranger version of emptiness. Places where the geometry of falling creates addresses. If you could place one mission at a Lagrange point, would you choose a cold telescope at L2, a solar storm sentinel at L1, or a probe drifting among the Trojan swarms at L4 and L5? Which parking spot feels most valuable, and which one feels most dangerous?